Boas model of atom. Niels Bohr modified Rutherford's model of atom and proposed a model for the hydrogen atom. The model explained the atomic spectrum of the hydrogen atom and the stability of the atom. Bohr's model is based on the following postulates. 1. Electrons revolve around the nucleus in concentric circular paths called orbits situated a definite distance from the nucleus. 2. There are stationary orbits for electrons. As long as electrons revolve in these stationary orbits, they do not radiate energy. The energies of electrons remain constant in stationary orbits. Different stationary levels, or stationary orbits, or shells are represented by capital letters K, L, M, N, with corresponding shell numbers 1, 2, 3, 4, 5, etc. 3. An electron can revolve only in those stationary orbits without radiating energy, for which the angular momentum of an electron is an integral multiple of h upon 2 pi mvr equals n multiplied by h upon pi, where m equals mass of the electron, v equals linear velocity of the electron, r equals radius of orbit, h equals Planck constant, n equals the integral number called principal quantum number, n equals 1 for K shell, 2 for L shell, 3 for M shell, 4 for N shell, etc. 4. Energy goes on increasing as stationary level goes farther from the nucleus. 5. A definite amount of energy, or quantum of energy, is absorbed when an electron jumps from a lower energy level to the higher energy level. Similarly, a definite amount of energy is given out when an electron jumps from a higher energy level to a lower energy level. The energy absorbed, or emitted, is the difference between energies of these two stationary levels. Drawbacks of Bohr's model. 1. Bohr's model fails to explain the atomic spectra for elements containing more than one electron. 2. When the hydrogen spectrum is observed by using spectrometer of high resolving power, it is observed that individual lines are not single, but consist of several fine lines lying close together. Such a hyperfine spectrum could not be explained by Boas theory. 3. The model fails to explain the splitting of atomic spectral lines in the presence of external magnetic field, Zeeman effect, and external electric field, Stark effect. Important features of Bohr's model. Bohr's model of atom successfully explained the atomic spectra of hydrogen and hydrogen-like atoms, and also provided a reasonable explanation to the stability of an atom. Following are the important features of this model. According to Boas theory, an electron neither gains nor loses energy while revolving in a particular stationary orbit. It implies that, if an atom is not disturbed, its electrons will go on revolving in the specified orbits forever, and the atom will remain stable. Energy of electron. The Boas theory enables us to derive an expression for the energy of an electron revolving in nth orbit. The expression derived for each atom is given below. En equals minus square bracket of 2 pi square m into z square into e raised to 4 upon n square into h square, square bracket completed, where En equals energy of the electron in the nth orbit. Z equals atomic number of atom. For each atom, Z equals 1. M equals mass of electron equals 9.10 multiplied by 10 raised to minus 28 grams. E equals charge on the electron equals 4.80 to 94 into 10 raised to minus 10 ESU. H equals Planck's constant equals 6.6256 into 10 raised to minus 27 UGS. Substituting the values, En equals minus 2.178 into 10 raised to minus 11 upon n square, UG per atom. En equals minus 2.178 into 10 raised to minus 18 upon n square, joule per atom. En equals minus 13.595 upon n square, electron volt per atom. As 1 electron volt equals 1.60 to into 10 raised to 19 joule. For hydrogen, like species, that is species containing only one electron, for example, helium plus 1, lithium plus 2, etc. The energy of the electron in the nth energy levels are also given by equations. Radius of Bohr orbit. As the electron of an atom revolves in one of the stationary orbital, the Coulombic force of attraction of nucleus of electron, that is Ze square upon r square, must be equal to centrifugal force of the electron mv square upon r. Hence, Ze square upon r square equals mv square upon r. Hence, r equals Ze square upon mv square. According to Bohr's postulates, angular momentum of electron, mvr, is integral multiple n of h upon 2 pi. Hence, mvr equals nh upon 2 pi. Or, v equals nh upon 2 pi mr. Substituting v in above equation, r equals n square into h square upon 4 pi square m z e square. Substituting values of h, m, z equals 1 for hydrogen, and E for the electronic charge, R, may be calculated as R equals 0.5 to 9 into n square angstroms. Thus for n equals 1, R equals 0.5 to 9 angstroms. N equals 2, R equals 2.116 angstroms. N equals 3, R equals 4.761 angstroms. N equals 4, R equals 8.464 angstroms. N equals 5, R equals 13.225 angstroms, and so on. This also suggests that electron takes up only discrete energy levels. Boas theory, and atomic spectrum, of hydrogen. According to Boas theory, the energy of electron, in nth orbit is given by En equals minus 2 pi square m into z square into e raised to 4 upon n square into h square. N takes up only integral values, like 1, 2, 3, 4, up to infinite, etc. N is called principal quantum number. The energy of electron varies with 1 upon n square. Hence, for n equals 1, E1 equals E1. N equals 2, E2 equals E1 upon 4. N equals 3, E3 equals E1 upon 9. N equals 4, E4 equals E1 upon 16. Hence, energy of electron does not change continuously. It changes discontinuously. Consider, now, the electron in the higher shell, and 2. The energy of electron in the shell N2 is given by En 2 equals minus 2 pi square m into z square into e raised to 4 upon and 2 square into h square. The electron emits quantum of energy given by delta E equals hv. And the electron jumps to shell N1. The energy of electron in shell N1 is given by En 1 equals minus 2 pi square m into z square into e raised to 4 upon n1 square into h square. So that the change of energy of electron and delta E equals En2 minus En1 equals hv. hv equals minus 2 pi square m into z square into east raised to 4 upon north 2 square into h square plus 2 pi square m into z square into e raised to 4 upon n1 square into h square equals 2 pi square m into z square into e raised to 4 upon h square into square bracket dot 1 upon n1 square minus 1 upon n2 square bracket complete. Or v equals 2 pi square m into z square into e raised to 4 upon h cube into square bracket of 1 upon n1 square minus 1 upon n2 square, bracket complete. The wave number corresponding to frequency bar V equals V upon C. Bar V equals 2 pi square m into z square into e raised to 4 upon h cube into c into square bracket 1 upon n1 square minus 1 upon n2 square, bracket complete. This equation is similar to the above equation of its combination principle for wave number of lines in spectrum of atomic hydrogen. Bar V equals R into square bracket 1 upon n1 square minus 1 upon n2 square dot bracket complete. R equals 2 pi square m into z square into e raised to 4 upon h cube into c. The value of R, the Rydberg constant, was reported to be 109,677.58 per centimeter. From known values of m, z, e, h and c, the new value of R was calculated to be 109,677.61 per centimeter. This is the greatest achievement of Bohr theory. Ionization potential of hydrogen. The energy required to remove an electron from the normal ground state of the atom is called the ionization potential. It is expressed in electron volt eV. For hydrogen, N1 equals 1, and if N2 equals infinite, that is, the electron is removed from the atom, then the ionization takes place. Hence, V corresponding to removal of electron can be calculated. Hence, frequency V equals CV, and ionization potential energy E equals HV can be calculated. Ionization potential, thus calculated using Bohr's theory, is in agreement with the observed ionization potential of hydrogen 13.60 electron volt. This is also success of Bohr's theory. Concepts of shells and subshells. According to Bohr's atomic model, electrons resolve around the nucleus in stationary energy levels called orbits. These orbits are also called as principal energy levels, or shells. These energy levels are represented by principal quantum number, n, which assumes only integral values, 1, 2, 3, etc. The shells are also represented by letters K, L, M, N, etc. The energy of the shell goes on increasing as the distance of the shell increases from the nucleus. For n equals 1, electron is present in the first shell K. For n equals 2, it is present in L shell, etc. The energies of electrons of the shells increase from K shell onwards. The number of electrons in any shell is given by expression 2n square, where n equals 1, 2, 3, etc. Hence, K level shell contains 2 electrons. L shell contains 8 electrons. M shell contains 18 electrons. N shell has 32 electrons. On this line, O shell has 50 electrons. And P shell contains 72 electrons. Subshells. Each shell is divided into subshells. They are designated as S, P, D, F. Each subshell, in a shell, is assigned an azimuthal quantum number L. For a given value to n, L can have n values ranging from 0 to n-1. For S subshell, L equals 0. For P subshell, L equals 1. For D subshell, L equals 2. For F subshell, L equals 3. Total number of subshells in a main shell, with a given value of n, is equal to n. It means, when n equals 1, then there will only one subshell, S, and L equals 0, for n equals 2. The number of subshells will be 2, S and P. L equals 0, 1. When n equals 1, shell will contain only one sublevel, that is 1s. L shell n equals 2 contains two subshells, 2s, 2p. M shell n equals 3 contains three subshells, 3s, 3p, 3d. N shell n equals 4 will have four subshells, 4s, 4p, 4d, 4f. This is summarized in above table. Principal shell, number of subshells, designation of subshells. K 1, 1s. L 2, 2s, 2p. M 3, 3s, 3p, 3d. N 4, 4s, 4p, 4d, 4f. O 5, 5s, 5p, 5d, 5f, 5 grams. The maximum number of electrons in a given subshell, given by 2 into 2 L plus 1. Thus, S subshell L equals 0 contain 2 electrons. P subshell L equals 1 contains 6 electrons. D subshell L equals 2 contain 10 electrons. F subshell L equals 3 contain 14 electrons. Dual nature of matter and light. Nature of light. Light is one of the form of energy. In order to explain the nature of light, Newton proposed a theory known as corpuscular theory. As per this theory, light is composed of the tiny particles known as corpuscles. This theory successfully explained the phenomenon of reflection, and refraction, but failed to explain the phenomena of interference and diffraction. Therefore, this theory was rejected. Wave theory. In 1864, Maxwell found that an alternating current of high-frequency radiated energy, in the form of waves, which traveled in space with the same speed as that of the light. Maxwell called these waves as electromagnetic waves, or electromagnetic radiations, because they were associated with both electric and magnetic fields. This gave birth to a new theory known as wave theory of light. The salient features of the wave theory of light are as follows. 1. Light is transmitted in the form of electromagnetic waves. 2. These electromagnetic waves are associated with electric and magnetic waves directed at right angles to each other, and also perpendicular to the direction of propagation of the wave. 3. All electromagnetic waves travel with the same velocity, which is equal to the velocity of light. 4. Electromagnetic waves do not require any medium for propagation or transmission. X-rays, gamma rays, ultraviolet rays, visible light, infrared radiations, microwaves, are different forms of radiation, and these forms propagate in the form of electromagnetic wave. Wave motion and its characteristics. Light travels in the form of waves. A wave is periodic disturbance in space, and wave motion represents the propagation of this periodic disturbance, which carries energy. A wave can be represented as shown in above figure. It is clear that a wave originates from the point of disturbance and propagates in the form of upward and downward movements. As the wave moves, amplitude of the wave goes on increasing till it attains a maximum value. This point of maximum amplitude is called crest. As the wave moves further, the amplitude decreases and attains a value 0 at the line of propagation on further movement. The amplitude decreases further on the negative side and attains minimum value. The point corresponding to the minimum value of the amplitude on the negative side is called the trough. Beyond this point, the amplitude again increases, and again we have a crest. Thus, a continuous sequence of alternate crest and trough is obtained during wave motion. 1. Wavelength, lambda. The distance between two consecutive crests, or two consecutive troughs, is called wavelength. It is represented by Greek letter, lambda. It is generally measured in angstrom unit, a, degree, or nanometer, and m. 1 angstrom unit equals 10 raised to minus 8 centimeters, equals 10 raised to minus 10 meter. 1 nanometer equals 10 raised to minus 9 meters, equals 10 angstrom unit. The other units of length are picometer, pm, 1 pm equals 10 raised to minus 12 meter, and micron, mu, 1 mu, equals 10 raised to minus 6 meters. 2. Frequency, V. The number of waves passing through reference point in 1 second is called the frequency. It is represented by Greek letter V, nu. It is expressed in the unit cycles per second, CPS, or Hertz, Hz. 1 Hertz equals 1 cycle per second. The unit kilohertz, kHz, and megahertz, mHz, are common in use. 1 kilohertz equals 10 raised to 3 hertz, equals 10 raised to 3 CPS. 1 mHz equals 10 raised to 6 hertz, equals 10 raised to 6 CPS. One single wave consists of 1 crest and 1 trough. Hence, a cycle is completed when a crest followed by a trough passes through a reference point. 3. Velocity, c. The distance traveled by a wave in 1 second is velocity of the wave. It is denoted by letter c. It is also the product of the frequency and wavelength. Hence, c equals v multiplied by lambda. Velocity of radiation equals frequency multiplied by wavelength. The velocity of all types of electromagnetic radiations, in space or in vacuum, is the same, and equal to the velocity of light. It is found to be equal to 3 into 10 raised to 10 centimeters per second, or 3 into 10 raised to 8 meters per second. Thus, all type of electromagnetic radiations travel with same velocity. However, they may differ from one another in their wavelengths, and hence in frequencies. 4. Wave number, nu bar. The number of waves which can be accommodated in 1 centimeter path of radiation is called wave number. It is represented by bar v, and read as nu bar. It is generally expressed in the unit per centimeter. Wave number of a wave is equal to the reciprocal of its wavelength in centimeter. Nu bar equals 1 upon lambda. It is possible to establish relationship between nu and bar nu as c equals v multiplied by lambda. Hence, lambda equals c upon nu, and nu bar equals 1 upon lambda equals v upon c. V. Amplitude, A. The height of a crest or the depth of trough from the line of propagation of the wave is called amplitude. It is represented by letter A. The amplitude of the wave determines the intensity, brightness of the radiation. Electromagnetic spectrum. The arrangement of different types of electromagnetic radiations, in order of increasing wavelength, is called electromagnetic spectrum. Wavelength of visible radiations lies between 400 nanometers, violet, to 760 nanometers, red. It forms a small portion of the electromagnetic spectrum. Infrared and ultraviolet radiations are on either sides of the visible spectrum. Figure illustrates the electromagnetic spectrum of radiation. Planck's quantum theory of radiation. The wave theory successfully explained the phenomena of propagation of light, but it failed to explain several other observed phenomena. For example, it could not explain the energy distribution in blackbody radiation and photoelectric effect. In 1890, Max Planck studied the energy emitted by hot bodies at different temperatures. He found that molecules of hot body emit light radiation discontinuously in the form of small energy bundles. This led him to propose a new theory, known as quantum theory of radiation. The silent features are as follows. Radiant energy is emitted or absorbed discontinuously in the form of small energy bundles or energy packets known as quanta or photons. This implies that radiations obtained from excited atom consists of stream of photons and not continuous waves. 2. Each quantum of radiation is associated with a definite amount of energy, depending upon the frequency of radiation. The energy E of a quantum is given by E equals hv, where V is the frequency of emitted radiation, and H is a constant known as Planck's constant. The numerical value of this constant is 6.626 multiplied by 10 raised to minus 34 joule seconds, or 6.626 multiplied by 10 raised to minus 27 erg-seconds. The energy of quantum of radiation can be expressed as E equals h into V equals h into c upon lambda equals h into c into bar v, where bar v is the wave number of radiation. 3. The body can emit or absorb energy only in an integral whole number multiple of a quantum. Thus, radiant energy can be emitted as hv, 2 hours v, etc. Photoelectric effect. When a beam of light of sufficient energy is made to fall on the surface of a metal, electrons are ejected. This phenomenon is known as photoelectric effect, and the electrons thus ejected are known as photoelectrons. Following are the observations. 1. The incident light must have certain minimum frequency to eject electrons from a particular metal. This frequency is known as threshold frequency, nu, 0. 2. The kinetic energy of ejected electron increases linearly with the frequency of the incident light, and does not depend upon the intensity of incident light. 3. The number of photoelectrons ejected increases with increase of intensity of incident light. Einstein's photoelectric equation. Albert Einstein, in 1905, explained photoelectric effect on the basis of quantum theory of radiation. According to him, when photon of certain energy, hv, strikes the surface of a metal, it gives its energy to an ejected electron present on the surface of a metal. If the frequency corresponding to the photon is equal to the threshold frequency V0, it gives its entire energy, hv0, to the electron. This energy enables the electron to come out of the surface by overcoming the attractive force. If the frequency of light is less than V0, then electron will not be able to come out of metal, and no ejection of electron will take place. When the frequency of light is greater than the threshold frequency V0, a part of the energy of the photon is consumed to separate the electron from the metal, and the remaining energy is imparted to the ejected electron, which acquires certain velocity v, and hence kinetic energy equal to 1/2 mv square. Einstein showed that hv equals w plus 1/2 mv square, where w is the energy required to overcome the attractive forces on the electron in the metal. It is called the threshold energy, or work function. 1/2 mv square is the kinetic energy imparted to the ejected electron. Since W equals hv0, therefore hv equals hv0 plus 1/2 mv square, or 1/2 mv square equals hv minus v0. This equation is called Einstein's photoelectric equation. Einstein was awarded Nobel Prize for Physics in 1921 for explaining photoelectric effect, and his significant contribution to mathematical physics. Dual nature of light. According to Einstein, light is composed of photons. A photon may be regarded as particles. Hence, explanation of photoelectric effect is in accordance to corpuscular theory of light, which assumes that light is composed of a stream of particles. Phenomena such as black body radiation can be explained on the basis of this theory. However, corpuscular theory fails to explain the phenomenon like diffraction, interference, polarization of light, etc. These phenomena can be explained only on the basis of wave theory of light. Therefore, nowadays, it is believed that light has a dual nature, that is particle nature, de-Broglie equation. Dual nature of electron. The properties of electron indicate that they have a dual nature. An electron behaves as both as a particle and a wave. Electron has mass, very small, and possesses kinetic energy. Hence, it should be a particle. At the same time, electrons can be diffracted, in the same way as light waves get diffracted. This is possible only when electron has a wave nature. This dual behavior of electron posed a big problem in deciding its exact nature. This problem was solved by a French scientist, Louis de Broglie, in 1924. Louis de Broglie suggested that all material objects show a dual nature. Every object which possesses a mass and velocity behaves both as a particle and as a wave. According to de-Broglie, the wavelength of a particle of mass m, moving with a velocity v, is given lambda equals h upon mv, where h is Planck's constant. The quantity mv represented the momentum of the particles. The above equation can also be expressed as lambda equals h upon p, where p stands for momentum of a particle. From the equation, it is clear that the wavelength of a moving particle is inversely proportional to its mass. Therefore, the heavier particles will possess much smaller wavelength as compared to lighter particles, like electron. Wavelength of electron. The mass of an electron is 9.108 multiplied by 10 raised to minus 28 grams, and its velocity is roughly equal to 2.99 multiplied by 10 raised to 1.0 centimeter per second. Therefore, according to the de-Broglie equation, the wavelength of an electron will be given by lambda equals h upon mv equals 6.626 multiplied by 10 raised to minus 27 upon 9.108 into 10 raised to minus 28 into 2.99 into 10 raised to 10 equals 2.43 multiplied by 10 raised to minus 10 centimeters equals 0.0243 Armstrong unit. Thus, wavelength is measurable and comparable to the wavelength of X-rays. Thus, electron is associated with a wavelength whose value is meaningful. Hence, electron can be treated as wave. Since electron possesses mass and a measurable wavelength, it should be regarded both as a particle and as wave. That is, electron has a dual nature. Heisenberg's uncertainty principle. The dual nature of electron posed some restrictions on the simultaneous and accurate determination of its conjugate properties, such as position and velocity, or position and momentum. Werner Heisenberg, a German physicist, pondered over this problem and proposed a principle in 1927, known as Heisenberg's uncertainty principle. This principle can be stated as follows. It is not possible to determine simultaneously the position and momentum of a moving microscopic particle, electron, with absolute accuracy. if delta x is the uncertainty in the determination of the position, and delta p is the uncertainty in the determination of momentum of a very small moving particle. Then according to Heisenberg, delta x into delta p equal and greater than h upon 4 pi, where h is a Planck's constant. The above equation can also be expressed as delta x into delta p equal and greater than h upon 4 pi m, because delta p equal to m into delta v, where delta v is the uncertainty in the determination of velocity, and m is the mass of the particle. From the equation, it is clear that the minimum uncertainty in the simultaneous determination of position and velocity, it is c equal to h upon 4 pi m. Hence, smaller the mass of the particle, greater is the uncertainty. Moreover, if delta x is very small, that is the position of a particle, is known more or less exactly. Delta v would be large, that is uncertainty in the determination of velocity would be large. Similarly, if an attempt is made to measure exactly the velocity of the particle, uncertainty with respect to the position will be large. Electron is a very small particle having almost negligible mass of 9.108 into 10 raised to minus 28 grams. Hence, the uncertainty in position and velocity for this microscopic particle is expected to be very large. For an electron, delta x into delta v equal and greater than 6.626 into 10 raised to minus 27 erg-seconds upon 4 into 3.14 into 9.108 into 10 raised to minus 28 grams equal and greater than 0.579 erg-seconds per gram. This value is very large in comparison to the dimensions of the characteristic quantities of electron and cannot be neglected. Hence, it may be concluded that the position and velocity, or momentum, of an electron can never be determined simultaneously and accurately. Concept of atomic orbitals. The essence of the quantum mechanical model of atom is a very important equation, known as Schrodinger wave equation. Del square psi plus 8 pi square m upon h square into E minus v into psi equal to 0, where E equals total energy of the system, V equals potential energy of the system, M equals mass of electron, H equals Planck's constant. In this equation, del square is an operator given by del square equals d square upon dx square plus d square upon dy square plus d square upon dz square. Here, psi is a mathematical function known as wave function. The psi in the above equation represents the amplitude of the electron wave. Square of the wave function, psi square, gives the probability of finding an electron at various places, in a given region around the nucleus. Psi square varies from one region of space to another. Thus, the probability of finding electron in different regions is different. This is in accordance with uncertainty principle. The Schrodinger wave equation is a second-order differential equation. It has several solutions. In order to have a quantum mechanical picture of the atom, the Schrodinger equation is solved for the given atom. This gives several values of wave functions. An acceptable value of wave function should be finite, single-valued, continuous, and should be zero at infinite distance. In order to get the acceptable values of wave functions, called eigenvalues, characteristic values of E called are used to solve the equation. The acceptable values of wave functions provide the regions around the nucleus, in which probability of finding an electron is maximum. These regions are called orbitals. The shapes of these orbitals can be obtained with the help of Schrodinger equation. The equation also gives certain specific numbers called quantum numbers, which specify the location of an electron in an atom. When Schrodinger wave equation is solved for hydrogen atom, the wave function psi is associated with electron having energy equal to minus 2.18 multiplied by 10 raised to minus 18 joule. Energy of electron in the Bohr orbit at the distance r from the nucleus is given by psi equals C1e minus Ceta r, where C1 and C2 are the constants. Distribution of electron in space is generally described in terms of function d, known as distribution function, and is given by d equals 4 pi r square, psi square. The distribution function d can be regarded as measure probability of finding an electron in spherical shell of thickness dr at various distances r from the nucleus. Substituting value of psi from above equation in and plotting the value of d against r, one gets probability distribution of electron density curve 4H in the above figure, while figure 3.16b shows cross-section of the electron cloud around the nucleus. Following conclusions can be drawn from figure A. The probability of finding electron at the nucleus is 0. B. The probability of finding electron increases as one moves away from the nucleus. At a distance of 0.53 angstrom unit, the probability of finding electron is maximum. It is called as the Bohr's first radius. C. On moving away from the nucleus, the probability of finding electron goes on decreasing and becomes almost zero at about 2 angstrom unit. It is evident that a precise description of the position of an electron in an atom is not possible. Hence, we adopt probabilistic description. We talk in terms of the probability of finding an electron at different points in the space around the nucleus. The concept of orbitals. When a Schrodinger wave equation is solved for a particular electron having a particular energy, a three-dimensional arrangement of points is obtained. The given electron can be found at these points. These are the points of negative charge. If these points are seen as a whole, a cloud of negative charges appears to exist around the nucleus. This cloud of negative charge is termed as electron cloud. The density of electron cloud is not uniform everywhere around the nucleus. There is a particular region in which electron cloud is more dense. For example, in hydrogen atom, the electron cloud is most dense at a distance of 0.53 angstrom from the nucleus. In this region, the probability of finding an electron is maximum. Such region is referred as an orbital. The three-dimensional region in the space around the nucleus, in which the probability of finding electron is maximum, is called orbital. In an orbital, there may be regions of high probability and regions low probability. An idea of this fact can be understood from the probability distribution curves of 2s and 3s orbitals. In each orbital, the electron has a definite energy. The energy of an orbital is lower if it is concentrated near the nucleus. The change in energy in going from one orbital to another is quantized. It is to be noted that an orbital is not the same as an orbit. The two differ in several respects. 1s orbital and n equals 1, Boas orbit of H atom, are shown in above figure.